Great presentation, very professionally done. For the next presentation, I'll be introducing the speaker, Mr. Jared Living. He will be presenting on the bomb calorimeter experiment that we conducted.
Hi, my name is Jared Living, and I'm part of Group 3, and I'm the reporter this time. And I'm going to be talking to y'all about what we did for the bomb calorimeter experiment last class. So the objective of this experiment was to take benzoic acid, which has a known heat of combustion, and place that in the bomb of the calorimeter experiment, and then use that heat of combustion as a means of calibrating the calorimeter in order to determine its thermal capacitance, and then use the thermal capacitance in order to determine what's the heat of combustion of an unknown fuel sample, which is peanut. And here's the experimental apparatus. Right here is the thermocouple, which was used in order to determine the temperature of the water in the calorimeter setup. And right here is the bomb container, which contains the fuel sample. And this is a crucible, which the fuel sample was placed in. And right here is the igniter wire, which served as a medium in order to ignite the fuel sample. And here was the stir, which was used to stir the water inside of the calorimeter. Now, the procedure was basically the calorimeter was comprised of the setup was comprised of the water, the nichrome wire, and the purpose of the water inside of the bucket of water inside of the calorimeter was to serve as a medium in order to determine the change in temperature from the ignition process. And before we did that, we put the fuel sample inside of the crucible, and we also put a small droplet of water in the crucible on the fuel sample. And what that served was just basically to saturate the atmosphere around the fuel sample so we wouldn't have to account for any type of vaporization from the ignition process. And by doing that, we were essentially dealing with lower heating value, which doesn't take into account vaporization, versus higher heating value, which does. And once we placed the fuel sample inside the bomb, we had to kind of depressurize and pressurize the bomb with oxygen at approximately 30 atmospheric pressure. And basically what that did was just kind of try to clean the air out, any excess air out of the bomb, so that there was predominantly oxygen left in the bomb, so to get the best result of combustion that we could get. Now, the variables we were solving for were the thermal capacitance of the calorimeter and the heat of combustion of the peanut. And the thermal capacitance is just basically, like I said, was a means of calibrating the performance of the calorimeter. And its units were in joules per Kelvin, energy divided by temperature. And the heat of combustion of the peanut was basically any type of energy per gram given off from a combustion process. And in order to do that, the governing equation for this was the first law of thermodynamics. As you can see up here, the heat of combustion times the thermal capacitance of the calorimeter times the change in temperature of the water. And basically what you need to keep in mind is some of the results I'm going to be showing you are going to be absolute value, but what you need to keep in mind is when you're doing this experiment that this is a exothermic process. So when you're using your heating values from the ignition process, you have to keep in mind the sign to keep it negative. It's not showing. I had a chart. Well, basically the results for the benzoic acid are displayed right here. The benzoic acid, its known heating value, its accepted heating value is approximately 26,430. You're probably going to see some different results. And the heating value which was given off from the wire, from the ignition process was minus 51 joules. So in order to get the complete heat combusted from the reaction, I had to divide this by the 0.95 grams of benzoic acid, which is what we use, and subtract 51 from that to get this result. And then basically use the equation I showed you from before in order to get this result as the thermal capacitance for the calorimeter. It's not showing my charts that I have right here. So then based off that, we were able to determine the heat given off on the peanut. And right here I used the initial temperature of 26 degrees Celsius, a final temperature of 28.3. And then we used 0.9 grams of peanut. And based off the wire that was burnt off, we were able to determine minus 44.27 joules for the wire. And then using the thermodynamic equation I showed you before, the same process for the benzoic acid, we were able to get an absolute value of 25,387.33 joules per gram for the peanut. And basically some of the other sections, they did a Rice Krispie treat, and this is the value that they got from that. As you can see, it's much lower. Its heat of combustion is much lower than the benzoic acid in the peanut. And based on some of the experiments which were covered out from the other groups, we were able to determine a mean value of approximately 25,138.85 joules per gram, and a standard deviation was approximately 2,900. And any sources of error could be, discrepancies in the oxygen that we put inside the bomb. I'm pretty sure y'all heard that loud bang. So that could have been a huge source of error right there. And basically it was just, this is the summary, trying to calibrate the calorimeter and then determine the heat of combustion of an unknown sample. And the significance of this experiment is that you can basically determine the heat of combustion of fuel samples, and based off that you can determine which fuel samples are best for the applications, like methane, propane, and other ethane, which have much, much higher heating values than the benzoic acid and peanut we used. So, that's pretty much all I got. Any questions?
So I know in the first law that work is involved. Can you explain why work cancels out in this experiment?
Why work cancels out?
Like Q minus W equal to the change?
All right, yeah, because there wasn't any significant change in volume of the system. So, the system was closed off. Tried to isolate as much, like I said, clean out as much air as we could, and just try to keep it within oxygen. So there wasn't any change in volume. So we were able to kind of exclude any work. And I don't know why, but my charts wouldn't show. But yeah, like I put a chart up here for temperature of the water versus time, and if they had actually shown, you saw how it kind of did a straight line and then shot up. That straight line was basically part of the experimental procedure, which we were basically kind of allowing the thermocouple some time to settle in and kind of get a feel for the temperature And it was basically kind of fluctuating between room temperature and the temperature of the water. Basically, you wanted the temperature of the water to be as close to room temperature as you possibly could get it.
If you compare the peanut volume, the peanut volume films with that original container, like the liquid volume,
I'm sorry.
if you compare your calculated value for the peanut film with that in the container, you can have the literature, the rules,
Right.
going forward.
To be honest, I couldn't really find an actual accepted value for peanuts, but one source.
If the container had like values, we can use like the
Oh, it did?
briefing value.
Oh, okay, I must have missed that on the container. But one accepted value that I was able to see was approximately around 23,000 that I was able to find. I forgot to look at the container to get the proper data for it. So this was a little bit above the accepted value that I was able to get, and yeah, and our mean was a little bit over that as well.
What about the standard deviation?
Oh, the standard deviation was approximately 2,900, so that's about how much. I used about 5 data sets from the data sheets that were posted on Google Docs, and the standard deviation from the data sets I used, including our own, was approximately 2,900 from the mean value.
2,900 from the mean value? That's a lot.
Yeah, I know.
What about the water we had in the water bath?
Right.
Do you think if we had increased the volume of water or using less volume of water, what's the effect of doing that?
Well, basically that would have kind of given the stir a little bit less work, because it probably, like the point of the stir, I forgot to mention this, but the point of the stir was basically to kind of keep the water at uniform temperature. And I think that probably would have helped maybe a little bit if you decrease it, because that's kind of less water that you're having to deal with. So I guess that's kind of an easier way to assure uniform temperature among the temperature medium that you were using.